We're back. So let's talk about some simple applications of the three laws. One simple application of the three law is as follows. Inertia. Something that wants to sit is going to sit. Okay? Just watch anything. Yeah, I'll watch my water bottle. Put it down. Okay, so just watch it and see what happens. And see if it has some inertia. Yeah, it's just still sitting there. It's not. Try this at home, kids, not for professionals only. Go and watch something. Just go look to your left. Left. Everybody look left. Oh, do you see that thing? Just watch it. Is it moving yet? No? Yeah, that's inertia, okay. Another application of the law of inertia. Spacecraft. Think about this. Let's say you want to get a space probe or a spacecraft someday with humans going to Mars. All right, so what do? You fire the rockets. You get it out of the pull of the Earth, get it out of the Earth's gravitational pull, and you shut the rockets off. You're good, you're done. Because what's going to happen? You get that thing going like 25, 26, 27 miles. It's like 30,000 miles per hour. That's enough to do it. That will leave Earth's gravitational pull. You can shut the rockets down. You don't have the rockets firing the entire time that you're going to send something to Mars. That's crazy. You can't carry that much fuel. As a matter of fact, the fuel that you need just to get out of the Earth's atmosphere is gone relatively quick. So what happens? Inertia takes over. Once you get it going, it keeps on going. It's like the Energizer bunny, going and going and going, until something stops it. We have sent probes beyond our solar system. All right, the Voyager 1, Voyager back in 77, I think that one was launched. We all remember where we were in 1977 when that was launched. We remember. And that is just, it's gone. It's been gone out of this solar system for a long time. And it's out there in the middle of like Spaceman. It's just out there. And it'll keep on going until it runs into some kind of a Klingon man-o-war spacecraft, which will blow it up for target practice. But it just keeps on going. There's nothing to stop it. All right? Inertia. All right. Newton's second law. Newton's second law is the mathematical law, and we're going to apply that so many times in the next several videos that you will get so tired of it. So we'll skip that one for now. Newton's third law, action-reaction. Try this, okay? Try this. It's just New Hampshire, right? I mean, so at least some of you ice skate. I mean, what else you got to do in the wintertime? You skate, you freeze, or or both, or you go outside and you ski. So many of you have been ice skating before, but try this, okay? Try this. Next time you're ice skating, just you're out there on the pond or something skating along, and find some little kid. Okay? This little kid. Find some. Relax, calm down. This is science, okay? So find some little kid. Now ask permission of the little kid. Say, excuse me, little kid, would you mind taking place in a very important science experiment? And of course, the little kid will kind of look at you and go, okay. All right, good, great, awesome. We're off to a good start. And then turn the little kid around. Okay, you probably shouldn't touch the little kid at this point. You tell the little kid to turn around, and he will. Okay, and now you get to touch him. Push hard. Raw! Push that little kid as hard as you can. Okay, maybe you shouldn't try this. Okay, maybe you might get in trouble. I'll leave this one for the professionals, okay? Be careful out there. So, but use your imagination. What would happen? That little kid's gonna go, wah, and take off. What's gonna happen to you? You know what's gonna happen to you. You are going to move backwards. So although you did the pushing, you pushed little kid, you went backwards. You can't go backwards unless a force in that direction was applied. Let's go back to Newton's second law. I said we're going to apply this many times. Here's something important about Newton's second law. The acceleration direction is always in the direction of the force. That's pretty simple, right? Think about that. You can't get something to move that way unless you apply a force that way. If I want to get something to move this way, I got to apply a force that way. Simple. So if I'm pushing little kid, then little kid takes off because I pushed little kid that way, but I went this way. There has to be a force this way. I pushed little kid pushed you back. So if you get, so if you do not heed my advice and do try this with some little kid that you don't know, you're going to get accused of, you pushed my child. And you can say right back to him, well, yeah, well, he pushed me as well. Yes, you can, because that's absolutely true. I actually used that on my kids one night. My daughter was about 2, and she used to drive my son, who was 3 at the time, nuts. She would take her finger and just drive it into his ribs while we were driving. And he'd, quit it, quit it. Dad, Leah's touching me. And I would say, well, according to Newton's third law, you can't be touched without touching back. So if Leah's touching you, you're touching her. Of course, I mess my kids up big time with science. It's awesome. Try that at home. Okay? He just kind of looked at me and blinked. No, I didn't. Yes, you did. Newton says so. You can't hug without being hugged back. You can't push without being pushed backwards. If you're going backwards, there's a force going backwards. You push, okay? It works. Boxers, you can hit somebody in the face with your hand. Break your hand. How did that happen? I hit face hits your hand. Okay, Newton's third law. You've got to remember that one because it'll come back to haunt you if you don't. Okay, so there are some examples of Newton's laws in everyday life that sometimes you don't think about. We just go around and we see this stuff happen, but we don't really think about why it's happening. And we have to think about why things happen in physics to be able to explain and do problems. All right, now, so we've gone over Newton's 3 laws. Let's start applying them mathematically. Okay, but actually before we do that, let's go into what are called free body diagrams. I do want to talk about those first. We are going to need to understand what's called a free body diagram. Okay, what's that? What's a free body diagram? So let's say that we have a box on a table. You're going to get so sick of me saying box on table example, but they're awesome. Okay, here is a table, here is a box. If you want to go with crate and be a rebel, put crate down, okay? And you want to go floor, be a rebel, fine, whatever. You want to be angsty like that, go ahead, America. You can do it. So box on table. Now, let's draw all the forces acting on the box. That's what a free body diagram is. It's all forces acting on the object that you are studying, that you're looking at. Free body diagram, all the forces acting on the object. Okay, so it's just sitting there. Are there any forces acting on it? Some of you might say, no, you said a force causes acceleration, and if it's just sitting there, it's not accelerating, so therefore there are no forces. Really? Universal gravitation? Yes, there's a force of gravity pulling on it, right? Gravity's pulling down on it, so let's draw that. Now, you will notice that whenever I draw a weight vector, because that's what gravity is, it's the force of weight, I always draw from the center of the object. It's called center of gravity. So draw your weight vectors from the center of the objects. That's typically where they are. Okay? Most things have a nice distributed mass, therefore the center of gravity is in the middle. So draw your weight vector. Now you label that FW. Okay? Force of weight, F sub W. All right, that's it. That's it, right? That's it. That's the only one. You already forgot Newton's third law, didn't you? Oh, you didn't? Okay, good. Well, I'm glad. So what is Newton's third law? For every force or action, there's an equal opposite force or action. So if the box is pushing down on the table, it's being pulled, so it puts a push on the table, what does the table do to the box? Pushes back equally. So we would draw this force going up equal, so I made them the same length, and opposite, arrowed up, arrow down. Equal and opposite, action, reaction, Newton's third law already coming into play. So this, I would label it as FW prime. FW prime, meaning the same but in opposite direction. Okay, now if the box is just sitting there, minding its own business, doing what boxes do on tables, then those would be the only 2 forces involved. That would be it. The only 2 forces involved, and we'd be done. If somebody comes along, though, and pushes on the box, we'd have to draw that force in. So let's go ahead and draw that force in. This is just an object that's sitting there, but there are still forces acting on it. It's not accelerating, because because these two forces are equal and opposite, and then there's no difference. Oh, that reminds me of something muy importante, grande. All right, I'm going to write it down for you. Here it is. F is equal to MA. All right, we know that. But this really means F net is equal to MA. What does that mean? That means in order to get an object to accelerate, you have to have a net force, an overall force that's unbalanced. We gotta write that down. This is important, and it's gonna mess you up if you don't remember this. Unbalanced force causes acceleration. Unbalanced forces cause acceleration. Look at this. It's an equal and opposite forces acting. That's not unbalanced, that's balanced. If you have balanced force, you will not accelerate. All right, now these are balanced forces. No acceleration. The box isn't moving. If I push on the box to the right, and I'll call that FP, and you can call it FP for F push, but us physics people, and therefore you, should know that it's called FP because the force is actually parallel to the table. It's parallel to the surface, so FP for parallel force. Or you can use pushing force if that works for you. So we apply a force to it. Will the box accelerate now? The answer is, according to this diagram, absolutely it will. It will accelerate. That's because there's no other force opposing this to slow it down or stop it. Now, if Angsty Billy is over on the other side, and Angsty Billy, I'll call this F sub B for Angsty Billy, he's pushing back with equal and opposite force, then those two forces would cancel each other out. They're balanced, so there is no acceleration. You need unbalanced force to cause acceleration. So let's say that Angsty Billy, although he's really angsty, isn't very strong. So Angsty Billy can only push with that amount of force. But you've been pumping the iron, yeah. I lift things up, I put them down, yeah. You've been pumping the iron, so you can push with this amount of force. You crush Billy like a bug, spit him out. That is unbalanced force. This box will accelerate to the right. Okay, to the right, to the right. Everything you own in a box to the right. I should write music. I got some great lyrics. I just gotta write them down before somebody steals them and makes a song out of my lyrics. So this is unbalanced, we would accelerate. Some of you might be thinking, hopefully you are, what about friction? What about friction? Would that be involved? Because there'll be some friction along the table in the box, right? There will be. But for right now, let's not worry about friction. It does become important and a little more complicated when we do it. For now, let's keep friction out of the picture. It's a frictionless table. And we beat Billy, we accelerate to the right. All right, Billy goes out and pumps some iron, and he, a year later, comes back and can push with this amount of force. Billy wins this time. So now we will accelerate to the left. I have unbalanced force. We get an acceleration. All right, okay, all right. This would be a free body diagram. If we had friction, we put the friction force a part of our diagram. But a free body diagram is what we're going to be using to consider what happens. It helps us visualize what's going to happen with an object. Okay, one more really kind of cool application of Newton's laws. This one's going to make your head go, what? Yeah, ready? Here we go. All right, remember, we need an unbalanced force to cause acceleration, therefore a net force. And net means overall, considering everything. Like net pay is after Uncle Sam takes all of the taxes. Thank you, thank you, thank you. You go from gross pay, which you made from your hourly rate times hours, to thank you very much, Uncle Sam. What you're left with is your net overall pay. The net overall force has to be unbalanced to get an acceleration. Okay, here we go. Apply this one. You have a cart. All right, here's a cart. There's a cart wheel, and there's my cart. And it looks like a cheese head, right? It's Green Bay Packer band. It's a cheese head. Some of you get that. So here we have a cart, And we've attached the cart to a donkey or a horse. Donkey, whatever works for you. Okay? And I'll draw my generic horse. And I'm going to put that up the donkey's butt there. All right, so there it is. There's my generic horse. Don't laugh at that. Don't laugh. You know, there's some very important things you learn in physics. And one thing is if you want to ever play the game Pictionary, which is the yellow category, which is people, place, or animal, and you want to win, you draw a generic animal and then go from there, and you will guarantee a victory for that round. What do you mean? What am I talking about? You know, Pictionary, drawing it. Okay, watch. Here we go. You ready? Generic animal. That's what you do every single time you're playing Pictionary. Boom. Dog. Mm-hmm. Okay. Yeah, right? Okay, here we go again. Let's do it again. Boom. Cat. Right? Okay, cat. Generic animal. It works every single time for every animal. You ready? Cow. We already got a horse. Generic animal. Draw them, you win at Pictionary. It's all about winning. Okay, second place is the first loser. Sorry. A lot of control there. But, what?
You know, it doesn't work for every animal. It doesn't work for a giraffe.
Yes, it does.
Okay, fine. It doesn't work for a snake.
Mm-hmm. Yeah, it does.
It doesn't work for a bird.
Mm-hmm. And if you want Pegasus, boom. Horse, bird, Pegasus.
It doesn't work for a shark.
Boom. Okay, dorsal fin. Camel. We can even go prehistoric on this bad boy. You ready? T-Rex. Okay, generic animal. Oh, I'm sorry, I went off on a tangent, didn't I? But I taught you something important other than physics. There are life lessons you'll learn here in this class, okay? Take that home. You'll never forget it. All right, where were we? Oh, donkey. Donkey is pulling the cart, right? So here's a case of brain exercise. If Newton's third law is correct, and donkey pulls on cart, therefore cart pulls back on donkey with equal and opposite force. So donkey is going to pull on the cart, cart's going to put Newton's third law. It's a law. It happens every time. Never been seen to be anything different. The cart's going to pull back on the donkey. That should cancel each other out. Forward force, backward force, cancel. Donkey can't pull cart. It's impossible. Donkeys, according to physics, cannot pull carts. Can't happen. Nope, can't happen. I don't care that I've seen it outside in real life, IRL. I don't care. I know it can't happen because physics, Newton's third law says it can't happen. Okay. That would be a misuse or misrepresentation of the law. You see, the law, Newton's third law, applies to an object. So we're looking at, so if I want to get an object to accelerate, I have to put a net force on the object. Okay, let's draw this out. I still don't know what you're talking about. Okay. All right. Cart pulls on donkey. That arrow represents the cart pulling back on the donkey. The donkey pulls on the cart. This arrow represents, is that equal? I want this to be equal. Equal and opposite force. It was third law. This arrow represents the donkey pulling on the cart. We want to get the cart to move. So all we do is we look at the cart. We don't care about the donkey. Oh, I mean, we do. I mean, it's a nice donkey. We care, of course. His name is Fred. Okay, we care about him. But I mean, we don't care about the donkey in terms of getting the cart to move. The only thing we care about is the forces acting on the cart if we want to get the cart to move. So we have to isolate our system, the cart. We want to get the cart to move. That's the cart. That's the donkey. The cart now has a force acting on it in that direction and nothing holding it back. Well, there'll be a little bit of friction. There'll be a little bit of friction, but the wheels certainly get rid of most of that friction. So there'll be a little bit of friction. Cart being pulled, friction holding back, cart's going to accelerate. You see, what we did there, and you say I tricked you, I kind of led you into that trick, where I had the equal and opposite forces, and I said cart can't move, right, because those balance each other out. But the truth is, the only thing we care about in getting the cart to move are the forces acting on the cart. So we look at the isolated cart, and we can see the cart will move forward. And of course, if we get a flat tire, or the wheel breaks and comes off, then we got a major problem. Donkey's gonna pull on cart, but with a butt-ton of friction holding it back. It can't move anymore. That's why wheels are actually a simple machine. They reduce the friction to very little. So we have very little friction holding the cart back. We will have the donkey's pull able to overcome that friction. Now, does this pull from the cart on the donkey affect the donkey? Sure it does. Donkey's got a harness and he's pulling along. Imagine the harness broke. What would happen to the donkey? Boom! The donkey would take off forward because there's no force holding donkey back. And the donkey has a lot of friction between donkey's feet and the ground. So if this were on ice, the donkey couldn't overcome the pull of the cart back on it because he wouldn't have enough forward push. The friction actually helps the donkey forward in this case. And the friction from the feet of the donkey, make that bigger arrow, is greater than the pull back from the cart. So the donkey has a lot of friction, not a lot of friction with the wheel. Equal pulls, but the donkey's friction push forward will overcome that pull back. And if this harness breaks, then then we got all this force going forward, and donkey goes, whoa, flying forward. So a trick question, but trying to get your brains to think. The equal and opposite forces, sure, they're there. But when we're looking at an object and talking about an object, we have to look at all the forces acting on the object. That's why we draw a free body diagram for the object. Okay, so is this free body diagram complete? The answer is no. I have weight going down, but I have equal and opposite force going up. Those two forces balance, cancel. That's why the cart doesn't take off into the air or go down into the ground, because those two forces are balanced. We don't have an acceleration up or down, but we do have that acceleration forward because of that being greater than the friction. All right. Whew. There's a lot of applications of Newton's laws. None mathematical yet. Oh, you just wait.